When most people picture the Apollo lunar module, they imagine that strange, crinkled exterior. The uneven gold foil, the exposed structure, and the asymmetrical panels give it a handmade appearance. But the truth is the opposite. The Apollo 11 lunar module, LM-5 Eagle, was one of the most mass-optimized spacecraft ever built. Every panel, every bracket, every tank, and every foil layer existed because engineers had shaved down the vehicle to the bare minimum. LM-5 had a fully fueled mass of about 33,000 pounds at undock, and only about 10,000 pounds of that ever reached the surface. Because the lunar module never flew through an atmosphere and never returned to Earth, Grumman Aircraft Engineering Corporation had enormous freedom to eliminate materials wherever possible. Beneath the gold foil was a precision-built spacecraft designed for a world with no air, no drag, and extreme temperature swings. In this video, we're going deep into the lunar module, Eagle's structure, its thermal systems, and the layered control architecture that guided Neil Armstrong and Buzz Aldrin to the surface. The lunar module consisted of two spacecraft, the descent stage and the ascent stage. The descent stage on Apollo 11 weighed about 14,700 pounds when fully loaded with propellant. It carried roughly 8,200 pounds of Aerozine 50 fuel and nitrogen tetroxide oxidizer. It also carried the landing radar, helium spheres pressurized to over 3,000 pounds per square inch, and 4 landing legs designed to absorb up to 10 feet per second of landing velocity. The structure was built from aluminum alloy beams with typical wall thicknesses around 50 thousandths of an inch. The ascent stage weighed approximately 10,300 pounds at undock and about 4,700 pounds after engine ignition. The pressurized cabin made up only a small portion of that weight. Nearly 30% of the ascent stage's mass was the propellant needed for lunar liftoff, about 2,400 pounds of hypergolic propellants stored in 2 spherical tanks, each around 40 inches in diameter. Together, the 2 stages formed a spacecraft unlike anything that had flown before. One half of it was designed to land and be discarded. The other half was designed only to operate in space. Inside the ascent stage, LM-5 looked surprisingly conventional. The internal frames were made from aluminum alloy 7075 T6, an aircraft-grade metal with a high strength-to-weight ratio. Many structural members were incredibly thin, often less than 1/10 of an inch, and bonded or riveted into a triangulated frame. The cabin pressure vessel panels were roughly 20 thousandths to 60 thousandths of an inch thick, depending on location. But where an airplane would normally have a smooth exterior skin, the lunar module did not. Engineers placed nearly all major tanks, plumbing lines, and wiring harnesses outside the cabin volume. The 2 large spherical ascent propellant tanks, the helium tank for the ascent engine, and all 4 descent stage propellant tanks were mounted in unpressurized compartments. The wiring harnesses running along LM-5's longerons stretched more than 700 feet in total length. Once the thermal blankets were removed, the entire lunar module looked like a skeletal aircraft. You could see the welded aluminum descent engine support beams, the avionics racks, the environmental control system equipment, and the bracket-mounted landing radar assembly. The spacecraft's odd outer shape was not structural. It was just a protective wrapper around an aircraft-style interior.
The strange, wrinkled look of LM5 came from its multi-layer insulation, or MLI. This insulation typically consisted of 15 to 25 alternating layers of aluminized mylar or Kapton film separated by Dacron mesh. On Apollo 11, the thickness ranged from half an inch in protected areas to over 1.5 inches in areas exposed to sunlit heating. Each film layer was only a few 10,000ths of an inch thick, far thinner than a sheet of paper. The entire blanket weighed very little, around 12 pounds per square meter, but provided massive thermal resistance. In space, LM5 experienced temperature extremes from over plus 250 degrees Fahrenheit in direct sunlight to below minus 250 degrees Fahrenheit in shadow. Without MLI, the propellant tanks would overheat or freeze, wiring bundles would become brittle, and the cabin would face dangerous thermal loads. Behind the insulating layers were thin micrometeoroid barriers made from aluminum sheets approximately 10,000ths of an inch thick. Even these sheets could stop dust-sized micrometeoroids traveling faster than rifle bullets. The insulation wasn't messy. It was meticulous engineering for a spacecraft that could never shed heat through air.
Inside the ascent stage cabin, LM5 maintained a pure oxygen environment at a pressure around 4.3 pounds per square inch, which reduced structural weight dramatically compared to Earth-like atmospheric pressure. The cabin volume was small, just 160 cubic feet, roughly the size of a compact car interior. The windows were multi-layered fused silica and tempered glass, each over 1 inch thick when combining all layers. They were shaped to minimize thermal distortion, and the forward triangular windows offered a 60-degree field of view, critical for manual landing. Crew restraints, storage compartments, and environmental control system hardware filled most interior surfaces. The cabin's walls were lined with aluminum honeycomb panels as thin as 1/2 inch to provide structural stiffness without mass penalties. The core of LM5's flight capability came from its multi-layered guidance and control architecture. This included the primary guidance, navigation, and control system, the Abort guidance system, the control electronics section, and the basic reaction control thruster valve switches. The entire guidance system had to maintain precise control of a spacecraft whose center of gravity shifted significantly during descent as the descent propellant tanks emptied. For example, LM5's center of mass moved by nearly 20 inches between undock and landing. The guidance system had to know exactly where the lunar module was, how fast it was moving, and how it was oriented, despite the constantly changing mass distribution. The primary guidance, navigation, and control system, developed by the Massachusetts Institute of Technology Instrumentation Laboratory, relied on a precision inertial measurement unit mounted on a gimbal platform. The primary inertial platform weighed about 30 pounds and consumed approximately 70 watts of electrical power. The Lunar Module guidance computer stored 2,048 words of RAM and 36,864 words of read-only memory. The computer's cycle time was 11.7 microseconds, and it could execute roughly 85,000 instructions per second. Though tiny by today's standards, it was more than capable of guiding the lunar module through powered descent. Data from the landing radar updated the computer once the lunar module descended below about 35,000 feet, allowing the guidance system to refine altitude and velocity. During the final phase of powered descent, the primary system controlled the throttle setting of the descent engine from 10% thrust up to full throttle, supporting the hover and landing maneuver Armstrong ultimately executed.
The Abort guidance system, developed by TRW, included its own inertial measurement unit, weighing roughly 18 pounds, along with a simpler digital computer that processed guidance commands at a much lower resolution than the primary system. Despite being less accurate, the Abort guidance system could still fly LM-5 into a rendezvous orbit if the primary system failed. The AGS operated continually during the descent, calculating its own estimate of position and velocity. Its accuracy was around 5,000 to 7,000 feet at lunar distances, compared to the primary system's accuracy of a few hundred feet. But it always provided a lifeline. The AGS was designed to survive severe electrical or computational failures. It had its own wiring harnesses, separate power feeds, and independent processors. It was the safety net beneath the safety net.
Below the computers was the control electronics section, a set of analog circuits that interpreted hand controller motions and converted them into pulse commands for the reaction control thrusters. Each thruster pulse could be as short as 14 milliseconds, allowing extremely fine control. The lowest level of control was the direct valve actuation switches. These switches bypassed computers and analog circuits entirely. When used, they energized the solenoids on the reaction control thruster valves directly. Each thruster in LM-5 produced approximately 100 pounds of force, and the 4 clusters were positioned to provide precise pitch, roll, and yaw control, even in the absence of higher-level systems. These direct controls were crude but reliable. They required almost no computational infrastructure and could be used even during severe failures.
The attitude controller assembly, the right-hand controller, was a small stick that provided rotational control inputs. The thrust and translation controller assembly, the left-hand control, managed throttle and translation. Each controller provided electrical signals in discrete detents, which the electronics translated into thruster firings. The hand controllers fed into the controls and display subsystem, which also incorporated inputs from the alignment optical telescope, the landing radar, the rendezvous radar, and both inertial measurement units. The landing radar transmitted at 9.6 gigahertz and provided altitude measurements down to a few feet above the surface. The rendezvous radar tracked the command module using a high-frequency beam capable of detecting it at ranges up to 75 nautical miles. All of these systems contributed to the cockpit displays, giving Armstrong and Aldrin real-time guidance cues during powered descent.
The descent engine on LM-5, built by TRW, could throttle from about 1,050 pounds of thrust at minimum to roughly 10,125 pounds of thrust at maximum. This deep throttling capability was new to human spaceflight and crucial for hovering and translating during the final 100 feet of descent. The Ascent engine, built by Bell Aerospace, produced about 3,500 pounds of thrust. It was a pressure-fed, fixed-thrust engine with no gimbal or throttle capability. The engine was designed with extreme simplicity, using hypergolic propellants, Aerozine 50 and nitrogen tetroxide, that ignited spontaneously on contact. The Ascent engine had no start sequence. It simply opened valves and fired. The reaction control system consisted of 16 thrusters arranged in 4 clusters. Each thruster produced roughly 100 pounds of thrust, and the 4-cluster arrangement ensured that the lunar module could rotate or translate along any axis. Together, these propulsion systems delivered exceptional maneuverability in space and during the final landing phase.
During the descent on Apollo 11, the primary system computed descent rate, horizontal velocity, fuel margin, and engine throttle commands. The landing radar began supplying data around 32,000 feet, allowing the computer to refine its estimates. Meanwhile, the Abort guidance system monitored everything. Its own inertial measurement unit sensed LM-5's motion, producing an abort trajectory automatically. If Armstrong had switched to the AGS at any moment, it would have guided the ascent. If both digital systems failed, the analog circuits remained available. And if even those failed, the direct thruster valve commands still gave the astronauts a way to orient the spacecraft. This layering ensured that LM-5 was never uncontrollable.
The inertial measurement units were mounted to rigid aluminum pedestals anchored deep within the ascent stage. These mounts were designed to maintain angular stability within a few arcseconds despite vibrations. The structural beams surrounding the IMU were designed to minimize flex during descent engine firing. The reaction control clusters were mounted on structural brackets aligned precisely along the spacecraft's principal axes. Any misalignment greater than a degree could create unexpected torque, so these mounts were machined and aligned to tight tolerances. The structure also had to handle the downward thrust of the descent engine. When LM-5 fired at full thrust, the descent stage structure absorbed over 10,000 pounds of force, distributing it through the welded aluminum frame and into the landing gear.
The multi-layer insulation on LM-5 protected delicate external components from severe heating and freezing. The descent propellant tanks needed to remain within a narrow temperature band. If they became too warm, tank pressure would rise dangerously. If they became too cold, propellant flow characteristics could change. The wiring harnesses could experience embrittlement or expansion without proper insulation. The helium spheres, pressurized to around 3,100 pounds per square inch, relied on stable temperatures to maintain correct feed pressure for the engines. The multi-layer insulation kept external surfaces within a predictable range, often maintaining a variance of only tens of degrees despite external swings of hundreds.
The entire lunar module structure represented a masterclass in weight reduction. Every pound saved increased mission safety. Engineers used aluminum honeycomb panels only a quarter-inch thick. Landing pads were covered in crushable honeycomb designed to absorb up to 19 feet per second of landing impact, though Armstrong touched down at less than 2. The ascent stage walls were so thin that astronauts had to be careful not to lean significant mass against certain panels. Wiring harnesses were cut to exact lengths. Even the paint was removed from most surfaces, saving dozens of pounds. The result was a spacecraft that looked unconventional but performed flawlessly.
Throughout all flights of the Lunar Module, including LM-5 on Apollo 11, every ascent engine ignited successfully. Every reaction control thruster operated within specification. The primary and abort guidance systems functioned exactly as designed. No lunar module ever suffered a structural failure or thermal protection failure. LM-5 Eagle landed safely at Tranquility Base and lifted off again flawlessly. The spacecraft achieved a perfect flight history across all missions. The Lunar Module remains the only crewed spacecraft ever built solely to operate in space and on the surface of another world. Its structure, insulation, and guidance systems were all engineered to meet one mission and one mission only. Beneath the gold foil was a precision machine optimized to deliver 2 astronauts safely to the Moon and bring them home again. Its unusual appearance was the result of thousands of engineering decisions focused on reliability, weight savings, and thermal control. LM-5 Eagle executed its mission perfectly and became one of the most successful spacecraft in history. If you enjoyed diving into the engineering behind the Apollo 11 Lunar Module, consider giving the video a like and sharing it with someone who appreciates real spacecraft design. It helps more than you think. And if you want more deep technical Apollo content every week, make sure to subscribe. This channel exists because of viewers like you who love the hardware as much as I do. Thanks for being part of the mission.